Hey everyone, welcome back to your search buddy. And in this video, we will talk about most important topic of quantum mechanics, which is particle in a box. Okay, which is also named as infinite square potential well or particle in a rectangular box. All right. Now, from this topic, you may got a question in different manner, like find out 0 point energy or ground state energy of particle in a box or infinite square potential well or particle in a rectangular box. You may have a question related to find out energy eigenvalues of particle in a box or infinite square potential well or particle in a rectangular box. You may have a question related to normalized wave function for particle in a box, infinite square potential well and particle in a rectangular box. Also, you may have a question having condition that if a particle is moving in a box having length L and height infinite. All right, so find out its energy eigenvalues and normalized wave function. Okay, so all these questions are related to a single topic, and this topic is very important. So let's talk about it. So what we need to do is consider a free particle of mass m confined to move in one dimensional rectangular box or square box, right, of height infinite, okay, and length capital L. Okay, so this is what we are considering. A particle is confined to move in a one dimensional rectangular box. So let's make a rectangular box with these conditions. So we have length, that is capital L. Total length from here to here is L. All right, and we know that according to our condition, height of this box is infinite. All right, okay, so if we are taking that a free particle is confined to move in one dimensional box, if we are taking one dimensional movement of any particle, so it may be along x-axis, y-axis or z-axis. Let's say we are taking it is confined to move only along x-axis, then x is equals to, so this condition is, it means particle is starting its movement from x is equals to 0 to x is equals to L. Okay, it means it can move along this complete length of the box. All right, now let us consider the balls of this box. Let us consider the walls of this box are rigid. All right, okay, rigid, elastic and non-penetrable. Okay, it means this particle cannot penetrate the walls of this box. As a result electron has to move inside the box like a free particle. Okay, so according to our conditions, electron or this particle moving inside the box like a free particle. Okay, now during its movement or during its motion, it may collide with the walls of this box. All right, so we are also considering that let the collision of the particle with the walls be elastic, right? So it does not, due to its elastic motion, it does not lose its energy. Okay, and due to this condition we can represent this via infinite square potential well condition. So let us represent this by a infinite square well potential, and according to this potential, the potential V is defined as, so we can define potential as, this potential is applicable only along x-axis as we are taking the moment, as well as the box is one dimension. Okay, so v of x is equals to 0 only if particle is inside the box, because particle is moving freely inside the box. It means there is no potential applied inside the box. X is greater than 0 but less than L, right? It means particle should be within this box, within this region, and only within this region we have potential 0. And second condition, we have an infinite potential where for x less than 0, it means particle in this region as well as in this region will experience a infinite potential. Okay, so and x greater than L. For these two conditions, we are getting that potential is equals to 0 when particle is inside this box, all right, and this potential is infinite if particle is outside this box. So outside we have two reasons. One is x is less than 0 and x is greater than L. Okay, these two reasons we are having, that is particle may be outside. So for the movement of particle from this box towards outside region, it will experience a infinite potential. Okay, so we can write it as potential here outside is infinite. All right, we have infinite potential. Also your particle cannot cross over this potential or this box because the height is infinite. Also we are taking the walls are impenetrable. It means particle cannot penetrate this one. If particle wants to penetrate this one, it will experience a infinite potential. So this is the condition we are having right now, and according to classical mechanics, if we want to solve this one, so let's take a classical view. If we want to solve this problem by using classical view, what are the findings according to classical? So classically the particle can have any value of energy, right? We know that classically particle have any value of energy. All right, if we are taking E is equals to 0, then particle will be at rest. Or this is a finding given by classical, that if we are taking energy is equals to 0, then particle will be at rest. If E is greater than 0, then particle will move along x-axis, as we are taking the moment only in one dimension. And at x is equals to 0 and x is equals to L, it will experience a force. It means at the balls of this box, the particle will experience a force and this force is equals to F is equals to minus dB by dt, where V is the potential. And since potential is infinite at the balls of this box, so force is also infinite. It means this force is also in the direction opposite to its motion, and it reflected from the balls and thus move back and forth. It means particle will move back and forth within this box due to this condition. So this is the classical result. These are the classical view to solve this kind of problem, that we may have any value of energy, and if energy is zero, then particle will be at rest but also inside the box. Okay, we are also taking this one. If this is the box we are having, then according to classical mechanics, if E is equals to 0, then particle will be at rest but also inside the box. Alright, and if E is greater than 0, then particle started its movement along x-axis. Particle will move along x-axis, and at the balls at here at x is equals to 0 and at x is equals to L, it will experience a force, that is F is equals to minus dB by dt. Since potential is infinite at the walls of this box, so force is also infinite. That's why it will move back and forth. Okay, so it will move back and forth at the walls of this box. So this is classical view. Let's talk about the quantum mechanical view. So we are taking quantum mechanical view, and let's start with the derivation of the real topic to our topic, that is by taking the Schrodinger's wave equations. Okay, we have already discussed about the Schrodinger's equation in previous lecture. So Schrodinger's wave equation for the wave function of a particle moving in straight line or in one dimension is given by, or moving in a straight line or one dimension is given by d square psi over dx square plus 2m over h cut square e minus v psi is equals to 0, right? And we know that let's say this is equation number 1. So as we know that inside the box we are taking potential 0. Okay, so now by taking potential v is equals to 0, that is particle inside the box so equation number 1 can be written as, our equation can be written as d square psi over dx square plus 2me over h cut square psi is equals to 0. This is my equation number 2. All right, now take k square is equals to 2me over h cut square. Okay, so we are putting this 2me over h cut square as a k square. All right, let's say this is equation number 3. So by using equation number 3 in equation number 2, what we are getting, d square psi over ds square plus k square psi is equals to 0. This is my equation number 4. All right, now this is something like a differential equation, and we know that every differential equation having a solution. So let's take a general solution of this equation, which may be written as the general solution of equation 4 may be written as psi x is equals to a exponential iota kx plus b exponential minus iota kx, which is equation number 5. And this is a generalized solution we are having where a and b are constants and which can be determined and to be determined by using boundary conditions. Okay, so by using boundary conditions we can find out the values of a and b. So to find out final solution to this wave function or this equation number 4, we need the value of a and b, and which can be determined by using boundary conditions. So right now, what are the boundaries? So boundary conditions we are having at x is equals to 0 and x is equals to L. So these two boundaries we are having. So let's apply the boundary conditions and find out the values of a and b. So we are having here boundary conditions, boundary conditions, and we have two boundary conditions. We have the wave function, first one is the wave function psi is equals to 0 at x is equals to 0. Also the wave function psi is equals to 0 at x is equals to 1. Okay, so let's apply first boundary condition, that is at x is equals to 0, the wave function psi is equals to 0. We are applying first boundary condition to equation number 5. So what we are getting, so equation number 5 can be written as, we can write equation number 5 as a plus b is equals to 0. If psi is equals to 0, can be write equation number 5 as a plus b is equals to 0, as at x is equals to 0, wave function is equals to 0. So we can write it as, and a is equals to minus b, or we can write it as b is equals to minus a. Let's say this is my equation number 6. All right, now using equation number 6 in equation number 5, what we are getting, we are getting psi x is equals to a e iota kx minus, again what we are putting, we are putting this b as minus a, so we are getting minus a exponential minus iota kx. All right, and I'm taking a outside, so here exponential iota kx minus exponential minus iota kx. All right, also multiply and divide. Okay, so I'm multiplying and dividing 2 iota. Okay, here in the right hand side, exponential iota kx minus exponential minus iota kx, and we are dividing it with 2 iota as well. Okay, now this condition, this part will become, so this is the property of sine. Okay, exponential iota x, so we know that exponential iota x minus exponential minus iota x over 2 iota is equals to sine of x. All right, so same property we are going to use here, and we got wave function is equals to 2 iota a sine of kx. All right, and wave function is equals to c sine kx. This is equation number 7, where c is equals to 2 iota a. All right, okay, so this is the value we are getting by applying first boundary condition. Now let's apply second boundary condition, and second boundary condition is at x is equals to L, again wave function is getting 0. Okay, So we have solved this one till equation number this 7. So we are just going to use, so equation number 7 becomes, we can directly use this condition in equation number 7. So this equation become 0 is equals to 2 iota, or we are taking c sine of kx. Okay, now we are putting x is equals to L, then above equation can be written as sine of kl is equals to 0, and we know that sine 0 or sine theta 0 is at n pi. So kl is equals to n pi, where n is equals to 0, 1, 2 and up to so on, right? So from here we can find out k is equals to n pi over L. All right, and this is my equation number 8. Now by taking square on both sides, what we are getting, k square is equals to n square pi square over L square. This is my equation number 9. All right, so I'm going to use this equation in equation number 3. Okay, so from equation number 3 we can write the value of k. All right, so k was the value of k, we have already derived it, that is k square is equals to 2me over h cut square. So what we need to put, equation number 3 in equation number 9. So by putting or by using equation on 3 in equation number 9, what we are getting, 2me over h cut square is equals to n square pi square over L square. Okay, so from here we can find out E is equals to n square pi square over h cut square over 2m L square. This is the energy value, or this is the energy for a particle in a box or infinite square potential well, where n is called quantum number, and since E depends on n, so let us denote, okay, since we know that the value of E is depending upon the value of n, so we can denote the value of energy, that is, let us denote the energy of the particle by En. All right, so we can write it as En is equals to n square pi square h cut square over 2m L square. This is energy value of energy, or formula for the energy, my equation number 10, right? And from here we can conclude that thus energy of a particle, that is En, is proportional to n square. This is first finding. Second finding, that energy of a particle inside a box with infinite heights and length L is inversely proportional to length of the box. Okay, and also this energy is depending upon, is proportional to mass. Okay, so it is length inversely proportional to length as well as mass, and proportional to n square. All right, so this is the energy relation. And okay, now what we need to do is to find out energy eigenvalues, as we have discussed during the starting of this lecture. We have also have a question related to find out energy eigenvalues. So what are the energy eigenvalues, or also what we need to find out 0 point energy or ground state energy. We are going to find out it here. So what we are taking, find out energy eigenvalues. So I'm writing it as energy eigenvalues, right? So what are the energy eigenvalues? Since we can find out from this equation number 10 as well, that when n is equals to 0, En is equals to 0, right? And corresponding wave function, that is psi n, is also going to be 0. It means particle is not present inside the box, and this condition is not true, as we know that particle is inside the box. So here we can write it as when n is equals to 0, according to equation number 10, the energy is also equals to 0. And if we are getting energy is equals to 0, then wave function corresponding to that is also 0, right? it means that it means that particle is not present inside the box, and this condition is not true inside the box, and which is not true, as we know that particle is present inside the box. We have already defined this one: infinite heights and non-penetrable walls. So particle should be inside the box, but when n is equals to 0, we are getting energy is equals to 0, the wave function is 0, and then we are getting particle is not present inside the box for if energy is equals to 0. Let's relate this with the classical result. So according to classical mechanics, if energy of any system is equals to 0, then particle will be at rest and inside the box. So this is contradiction between classical result and quantum result. That's why classical results is not able to explain such kind of phenomenons like photoelectric effect, Compton effect, and black body radiation, because all of these topics is related to energy. And in case of this particle in a box itself, according to classical mechanics, if you are getting En or energy is equals to 0, then classical mechanics saying that particle will be at rest and inside the box. But if we are relating this with quantum mechanics, we are getting if n is equals to 0, energy is also going to be 0, and then particle is not present inside the box. But we are getting that particle is inside the box, because particle cannot penetrate the walls, it cannot cross over the walls, so particle should be within the box. So that's why we are getting contradiction between classical and quantum result, and that's why the quantum results are more validate as compared to classical results, right? So by using this statement, we can find out lowest energy value of a particle in infinite potential well, which is at n is equals to 0. We are not getting lowest energy value at n is equals to 0, as in that case energy is going to be 0. And if energy of any system will be 0, that system will not be existed. But right now the system is there, we are having a particle inside the box. It means there is existence of electron inside the box. Okay, so we can write it as, so the lowest value of energy. Okay, so the lowest value of energy of particle in a box or infinite square potential well, particle in a box, or or infinite square potential well. Okay, is at n is equals to 1. Okay, this is called ground state energy, ground state energy, or 0 point energy. Okay, that's why we took it as a question to us, that is called ground state energy and 0 point energy. So if any question you are getting, or you need to find out 0 point energy or ground state energy, you just need to mention that at n is equals to 1 we are getting 0 point energy, and this is equals to, so for n is equals to 1, what we are getting, the value of En according to equation number 10 will be minimum. So minimum energy of a particle in a box we are getting n is equals to 1. So we can mention it as E1 is equals to, as we are putting n is equals to 1 in equation number 10, what we are getting, so 1 square is equals to 1 pi square h square over 2m l square, and this is my equation number 11. All right, this is called ground state energy and 0 point energy, right? So this is the ground state energy or 0 point energy, and corresponding higher energy state is called excited energy states, right? So the energy corresponds to higher states is called excited energy, and states are called excited states. Excited states then, and these excited states are given by, so we are getting at n is equals to 2, we got E2 is equals to 2 raised to power 2 pi square h square over 2m l square, and we can write it as we know that this part pi square h square over 2m l square is equals to equation number 11, which is showing E1. So we can write it as this is equals to 4 times E1, as 2 square 2 is equals to 4 times E1. It means energy is getting increased for the higher energy state from the ground state, right? At n is equals to 3, E3 is equals to E3 is equals to 3 times, okay, we are getting pi square h square over 2 ml square, and this is equals to 9 E1. And for n is equals to 4, E4 is equals to pi square h square over 2 ml square, which is equals to 16 E1, and so on up to nth value we can find out, and so on up to n values. All right, sometimes you may got a question related to find out first excited state for a particle in a box. So this will be the first excited state for a particle in a box. As n is equals to 1, we are getting ground state. Then first excited state, this is first excited state. So you may got a question from here that find out first excited state for a particle in a box or infinite square potential well. Okay, still we have left with last question related to here, that is what we need to find out is the normalized wave function. So let's find out the condition for normalized wave function. Let's talk about the normalized wave function. So wave function of a particle in a box. So let's start from equation number, I think from equation number 7. Okay, so from equation number 7, that is, what was the equation number 7? So we got equation number 7 as this psi x is equals to c sine kx. So we are getting psi x is equals to c sine of kx. This is our equation number 7. Now we know the value of k, and we have already found the value of k, which is equals to n pi over l. Okay, according to equation number 8. So use equation number 8 as well here. So by using the value of k, which is equals to n pi over l. Above equation can be written as psi x is equals to c sine of n pi x over l, right? Now we know that probability density, now we have already defined this in previous lectures, that probability density, let's say we are representing this with p is equals to always psi star psi, and psi having movement only along x axis, so this is psi star x, or psi x, you can write it as psi x, and there is a star between these two we are taking, and we know the value of psi x is equals to c sine n pi x over l, right? And also c sine of n pi x over l. It means we are taking the multiple of complex conjugate pairs, right? So right now there is no complex equations we are taking, so the value of psi will be equals to this one. And if we are getting iota in this equation, then psi will be the complex conjugate. It means you need to write it in a reverse manner, but right now we are not having psi as a complex pair. Okay, so this is the probability we are getting, and from here we can find out that psi star psi is equals to c square sine square n pi x over l. All right. Now, since the probability of finding the particle in between this region, that is x is equals to 0 to x is equals to L, is 1. Okay. So, within this region, what will be the probability of finding the particle is 1, right? So, we can write it as, since the probability of finding the particle between x is equal to 0 to x is equals to L is 1, right? Because particle is somewhere, because particle is somewhere within the boundary, right? So that is, we can write it as, we have a boundaries from x is equals to 0 to x is equals to L, and probability density d of x, only movement along x axis, is equals to 1, because probability of finding the particle inside this box is 1 in within this region, that is from x is equals to 0 to x is equals to L. All right, so we can write it as, or 0 to L directly use above relation, that is this relation here, the value of psi star psi is equals to c square sine square n pi x over L, and d of x is equals to 1. All right, I'm taking c outside, so this is 0 to L sine square n pi x over L, d of x is equals to 1. So by using solution to above integral from integral table, we got the value of c square is equals to 2yl. All right, and from here we can find out c is equals to 2yl under root. Okay, so by using the value of c in equation number 12, that is this wave function is equals to c sine n pi x over L, we got that normalized wave function. So normalized wave function inside the well or a box is given by psi is equals to 2yl under root sine of n pi x over L, right? This is the wave function or normalized wave function for a particle in a box or infinite square potential well. So this complete derivation is there, and you will get this question for maximum marks. Okay, I hope you are able to get it. If you have any question related to this topic or any topic, you can comment below. Thanks for watching this video. I'll see you in the next one.